Hi everyone, welcome back to all of you on my YouTube channel. So I'm Ankit Mishra. I'm teaching for Gate Chemical Engineering for since last 3 years. In previous lecture, in the process and control lecture, first I have discussed about the fundamental concept related to the Laplace transform and the motivation regarding process dynamics and control. Where I have discussed about this why we are using the control system in this to maintain the temperature, outlet temperature of the reactor, or optimal temperature for the optimum conversion for the reactor system. And after that we have discussed you can make a closed loop kind of things, and we will be solving these things in the subsequent lecture. And after that I will started doing the Laplace transform, where I have discussed the fundamental functions of Laplace transform. And after that I have also started transform of derivatives, where I have done the Laplace transform of first order, second order, and nth order derivative, right? So in today's lecture I'll be talking about why we are using this Laplace transform to solve the differential equation, because we have seen that Laplace transform provides a flexibility that we can transform any derivative in the S domain, and how this S domain conversion from Laplace transform can be used to solve the differential equations. So let's see, I'll start these things with a question only. So let's say if we have a question of d3x by dt cube plus 4 dx square divided by dt square plus 5 dx by dt plus 2x will be equals to 2, right? So this one is the Laplace ordinary differential equation of the third order, and we want to solve this thing. So let's say boundary condition has been given to you. Let's say x0 will be equals to dx0 divided by dt, that is equals to d2 x0 divided by dt square, that is equals to 0. And if value of function x0 is equals to x dash 0 is equals to x double dash 0 equals to 0. So these things are given to you, and now you are supposed to solve these things. You want to calculate the value of x in terms of S domain, right? So let's say if I'll do this integration solution. So if we have d3x by dtq, you can write sq xs minus s square x0 minus s x dash 0 minus x0. Is that clear? And we have the value x0, x dash 0, and x double dash 0 is 0. So if you will substitute this value, so you will be getting d3x divided by dtq, that is equals to x3 xs. Now if we take the Laplace transform of d2x, so Laplace transform of this one, and Laplace transform of d3x by d2x by dt square, so you can write s square xs minus s x0 minus x dash 0. So again you are supposed to, this value is 0, this value is 0, so you will be left with s square xs, s square xs. And now if I want to write Laplace of dx divided by dt, that can be written as s xs minus x0, right? So if this will be 0, then you will be left with s xs. Okay, so now you have all of these values. So once you will substitute all of these value in the equation, so you can write, if we take Laplace transform for both sides, so taking Laplace transform both sides, so I can write Laplace of d3x by dtq plus obviously Laplace of d2x divided by d2 square plus Laplace of dx by dt, plus there is a constant value Laplace of 2x, that is equals to Laplace of 2. Is that clear? So once we will substitute this value, you will be getting, so for this we have left with only sq xs, here sq xs plus s square xs plus s xs plus So here it was 5s xs, 5 into s xs plus 2 xs, that is equals to Laplace of 2 is your 2 by s. Is that clear? So now if we'll take common xs, so you will be left with s cube plus s square plus 5s plus 2, that is equals to 2 divided by s. So you are supposed to calculate the final value xs, that is equals to 2 divided by s into s cube plus s square plus 5s plus 2, right? So this one is the value that you are getting from here. I hope this is clear, right? Now this is one thing. Second thing is that in the subsequent lecture I will be telling you how to calculate the value of xs into xt, right, to find out the dynamic response of the system at every time, right? So with in coming lecture you will be able to calculate all of these things also. So I'm going to another questions of today's discussion. Let's say if you have a question like dx divided by dt plus 3x, that is equals to 0, and if you have the boundary condition x0 is equals to 2, you are supposed to calculate the value of x. So this is very simple ordinary differential equation. You can solve these things in like dx divided by x is equals to 3 dt minus 3 dt, and you can integrate and you can solve like ln x is equals to minus 3t plus c, and you can substitute the value. But how we can use the Laplace transform in order to solve these things? So I can write Laplace of dx divided by dt plus Laplace of 3x, that is equals to Laplace of 0. Is that clear? Sorry, Laplace of 0. So this will give you s xs minus x0 plus 3 xs, that is equals to 0. So I can calculate. Now we can substitute the value here. So if I'll take common x s, so you will be left with s plus 3, and that is minus 2, that is equals to 0. So the value of xs, that is equals to 2 divided by s plus 3. Is that clear? Okay, so this is what we are going to get it now. So again this value can be calculated like that. This is in the x domain, and again from here you can take Laplace inverse of xs, so you can calculate Laplace inverse of 2 upon s plus 3, and so on and so forth. You can calculate all of these value as well. So this is how you can calculate these things. This is very very important. So similarly I am writing one question here. I won't be solving, but these questions can be helpful if you solve these things at your home, right? So let's say if you have a question like x double dash plus 4x dash plus 3x plus 5 equals to 0, and if you have a boundary condition x0 is equals to x dash 0 equals to x double dash 0 equals to 0, so you can solve these things. This is a second order ordinary differential equation, and with the help of Laplace transform you can calculate these things. Is that clear? So lots of these things are there, and you are supposed to calculate this kind of problem in your examination, and definitely you will be getting it. I hope this is clear to all of you. Now coming to the next problem of Laplace transform is you can linearize the Laplace transform. So if you have two functions, so let's say properties of Laplace transform. So first properties of Laplace transform can be written as Laplace transform is linear. What do you mean by this linear thing? Just try to understand. If I am taking Laplace transform of a function a into f1t plus b into f2t, that can be written as a Laplace transform of f1t plus b Laplace transform of f2t. Is that clear? So these are the things that is there. Okay, now second thing is that So based on this particular concept, you can see numericals are coming in the competitive examination and you will be able to solve, right? So how the questions come and what kind of questions that can be there on this particular topic, let's try to understand. So let's say if you are supposed to calculate Laplace transform of 2t plus 3 sine 5t. So these are the two functions, this is f1t and f2t. So I can write Laplace of 2 into Laplace of t plus 3 into Laplace of sine 5t. So that will be equals to 2 divided by s square plus 3 into 5 divided by s square plus 5 square. Is that clear? So finally you will be left with 2 upon s square plus 15 divided by s square plus 25. So this is how you can calculate these things, and you can use the function or concept that Laplace transform is linear, and there is a combination if Laplace two function are the linear combination in the form of linear combination, and you can take the Laplace while separating the function, something like that I told you. Now coming to the another part of this lecture, and that is the transform of a simple function, right? That is also very important concept. Transform of simple function. So let's first try to understand the simple function is the step function. So these functions will come when we will be solving the some gate previous year question, as well as in further topic when we will be giving some different kind of inputs to the process, and then you will see based on the step input, ramp input, or all of these functions will be there, because this is the part of input system, and from there you will be understanding the dynamics of the system. So let's see how these step function look like. Just thank you. Yeah, so let's say if there is a function ft that can be written is in this form: 0 when t is less than equals to 0, or sorry, t is less than 0, and the value is 1 when t is greater than 0. Or I am not writing m, so 1 I am writing m. That is the magnitude of a step input. So how does it look like? So if you see the step input, something like that, so the plot should be like that. So if this is time axis and if this is the functional value, so when here let's say I am assuming t equals to 0, so till this time the function value will be 0. Let's say this I am showing it in the green color, and at t equals to 0 there will be a step input of magnitude m, and it will go like that, right? So this value is m. So where you can say that m is the magnitude of a step input, correct? This is how the step functions look like. And now sometimes what happens when m equals to 1, then this is called as the unit step function, because magnitude is 1, that is called as a unit step function. Then ft will be called as ut. So wherever you see the ut, then this is called as the unit step function. So this is called as the unit step function. Is that clear? Now if I am taking the Laplace transform of m, so that will be equals to m by s. Is that clear? And if I am taking Laplace transform of 1, so that will be equals to 1 by s. So based on this value you have to differentiate whether this is a step input of magnitude m, and whether there is a step input of magnitude 1, and which is called as the unit step input, right? So every time it may be possible you want to be getting unit step input, there will be some magnitude of step input associated with that. That's why you can use this thing. Now sometimes let's say if you are supposed to calculate Laplace transform of 5 into ut, right? So you can write 5 is a constant that will come out, and Laplace transform of ut. So that is 5 divided by s. So here you can see, if I multiply 1 divided by m, 1 multiplied with m, that is m. So you are giving a magnitude of 5 to input. So that's why this is also called as the step input, and unit step input is multiplied with 5. So ultimately this is a step input or a step function, right? So this is how these things look like, right? Now, so sometimes how does this look like? So you will see there is a notation. If I write a proper notation, of a step function. So if I am taking ft is like m multiplied with ut, right? Ft is equals to m multiplied with ut. Okay, so where m is the magnitude of input, or sometimes obviously it will be working as input. That's why it in subsequent lecture I will be writing it as an input, right? This is how these things look like. Now coming to the second function, the exponential function. So these are the very fundamental thing in process dynamics and control for chemical engineers, but this is very, very important, and this will build a good base for solving a good problem in the process dynamics and control. So let's say, how does it look like? So let's say if ft is a function and having magnitude when t is less than 0, and having magnitude e to the power minus at when t is greater than 0. So this can be also written as ut into e to the power minus at, right? So ut is unit step function which is being multiplied with the exponential function having e to the power minus at. Is that clear? So let's say if I am talking about Laplace transform of ut into e to the power minus at. Is that clear? So again, it can be solved while using the fundamental equation, that e to the power minus st into ut into e to the power minus at dt. Is that clear? So ut is 1, so directly it can be written as 0 to infinity, and e to the power minus s plus a t and dt. So that can be written as 1 upon s plus a, right? So if you see, recall these things, Laplace transform of e to the power minus at used to be 1 upon s plus a, and here you have also seen Laplace transform of ut into e to the power minus at. We have also seen this is coming as s plus a. So the meaning of unit step input is that the magnitude is 1 and there is nothing associated with it, right? So only it can change the magnitude. If I multiply ut by 5 or some magnitude m, then only it will change the magnitude, and it will look you will get this kind of thing, right? Now coming to the next function, that is called as the ramp function. This is very, very important function and a bit confusing. So coming to the third one, that is a ramp function. So if I am denoting, or if I am writing a function like ft, that is equals to 0 when t is less than 0, and which is equals to t when t is greater than equals to 0. So just see how this thing, and this can be also written as t multiplied with ut, means I am multiplying a step function with the magnitude of t, and then it will become a ramp function. So if you want to plot this function like that, so it will look like in this way. So let's say if this is my function and having time, so it will go like up to here when t is equals to 0 is 0, and having a slope of 1 year, right? So yeah, so it will go like that, because if you are not going to multiply anything here, so the slope is 1. That's why this is a step ramp input. Is that clear? Now when we do the Laplace transform of ramp input, Laplace of t into ut, right? So that can be written as 0 to infinity t into ut into e to the power minus st dt. So in previous lecture already I have solved these things and we were getting 1 upon s square. So the Laplace transform of unit ramp input or unit step function, unit ramp function, because here magnitude is 1, right, 1 multiplied, because here this is 1 only, right, that's why this is a unit ramp input. There may be some magnitude associated with it, I'll tell you later on in the next lecture, but here you will see how these kind of inputs can be associated with a particular problem, and whenever this is there in the problem, you have to understand how the input is going to vary. So the value of input was 0 when t was less than 0, and it was going or it was rising with a magnitude of 1, and along this direction having slope 1, slope y where 1, that means the theta will be equals to 45 degrees, something like that. Okay, this is how these things look like. Now next thing is that is very very important thing, and that is the heart of the process analysis and control, that is the transfer function. And whenever we will be solving a dynamics of any system, we are supposed to calculate the transfer function, and based on the transfer function only we can categorize whether this is a step input, ramp input, sinusoidal input, or impulse input, something like that, and based on that only you can calculate these things. So let's try to understand the transfer function. Right now here if you see, we had a process. In my first lecture you have seen these things. There was a process, and in this process, let's say this one is your process, and I'll be giving any input to this process, and we are expecting there is some output from this process. Is that clear? Okay, so this is how this transfer functions things work, right? So we have input, the process will happen in some kind of system, and after that we will be getting output. So what is Laplace transfer function? Transfer function is a Laplace transform of your output variable divided by your Laplace transform of your input variable. This is very very important concept, and this is not very difficult. Whenever you will be solving the dynamics of any system, every time you will be calculating the transfer function. Is that clear? So let's say we have a process. Just try to understand here. I'm giving you a simple example to let you understand this thing. So let's say we have a process here, and here we have an input of, let's say, 5 divided by s square. This is our input and this is our output, and having transfer function is 5 upon s plus let's say 3. Is that clear? So if I want to calculate transfer function of process, so I'll be denoting it as GP. If GP is there, that is transfer function of the process, and that is equals to output divided by input. So Laplace transform, why I am typing, so this should be in S domain, that's why I am telling you domain, and this should be also in S domain. So here obviously the function is given in S domain. If you will see here, 5 divided by s square and 5 upon s plus 3. So now directly I can write 5 upon s plus 3 divided by 5 divided by s square. So 5 will get cancelled out, and finally you will be left with 1 upon s square into s plus 3. So this is how the transfer functions can be written, that the transfer function of output and input, both you have to convert into your S domain, and when you divide output response by input response in S domain, that will give you a transfer function, right? Now coming to the next problem and next concept, that is the initial value theorem. That is very very important. Initial value theorem. So let's say I am assuming this x is my input and y is my output. So throughout the whole course I'll be assuming this kind of notations. Whenever I am writing x, that should be input, and y, that should be output. This is inbuilt. But let's say if I will be denoting some specific input, I'll write this is my input, something like that, right? Now so if I am calculating y t is equals to 0, this will be my initial value, and when y t tending to infinity, that will be equals to my final value, right? This is how these things like. So what initial value theorem says, that limit t tending to 0 yt means initial value of function that will be equals to, in t domain, limit yt t tending to 0, that will be equals to limit s tending to infinity s into fs, right? So let's say if you want to calculate the initial value of any function, but you have a transfer function in s domain, so directly you can substitute limit s tending to infinity s into fs, and that will give you the initial value of the transfer function, right? Or initial value of the process. So this is the initial value, right? Now what final value theorem says, now next one is the final value theorem. What final value theorem says, that the final value limit t tending to infinity yt, that will be equals to limit s tending to 0 s into fs, right? So this is the final value. Output, is that clear? Now but there is a limitations here. So this is the final value, so there is a limitations. This is only valid when output response of the system is stable, right? If it is unstable, you cannot use the system, right? First thing. Second thing is that what is the stability and instability in the system? Here I won't be discussing. When I'll be entering to the stability criteria of a particular dynamic control system, there I'll be letting you how, when a system will be stable, when a system will not be stable, while using Rao-Thierry or Bode stability criteria. There you will learn all of these things. But right now I'll tell you in the subsequent next lecture how can you understand whether the system is stable or not, to use or to understand this initial and final value theorem. Okay, I hope this is clear to all of you up to here. In the next lecture I'll be discussing some question or some concept regarding the initial and final value theorem as well, to understand when we can use the initial and final value theorem for a particular function or for a particular input and output, something like that. And after that I'll also discuss about the limitations of final value theorem and initial value theorem while calculating the roots of the denominator, something like that. Okay, see you in the next lecture. And if those who have not subscribed my channel, please go and subscribe, and don't forget to press the bell icon, so let's so that if I'll put any video, you'll be getting the notification for that video. And also share among your group, so that those people who are unable to afford the quality content on any paid courses, they can avail these kind of concept over here. And definitely it is going to help you a lot in your BARC examination, GATE examination, as well as the examination which is going to happen this year in 2025 for assistant engineer in Bihar engineering, right? Assistant engineering Bihar through BPSC. Okay, thank you, see you in the next lecture.